Okay, today we're going to discuss the homework that's due on October 18th. I believe it is problem set 8, though it hasn't been marked. It is, thank you. So the first problem is a two-dimensional collision problem. The first problem you're going to have to face is the fact that the velocity 1 as a vector is 80 x hat miles per hour. So the first thing you need to do is convert that to meters per second. And then velocity 2 is 40 y hat miles per hour, and you need to convert that also into meters per second. I don't know why I stuck with miles per hour. They collide and stick together. How much energy is lost, and what is the velocity and direction of the car truck? So V2 looks like this, and V1 looks like this. Not to scale. But the other thing is that momentum can be used as a vector as well. Now, we have the advantage of they're traveling at right angles to each other, so that when they stick, they have a momentum and a velocity vector. The thing that you have to do is this third vector is in reality P1 x hat plus P2 y hat, where P1 is M1 V1 and P2 is M2 V2. So it's a very simple vector addition problem. Now you know one of the objects is heading to the right, the other object is heading up, so it's going to have a total momentum that is up and to the right. The total momentum P3 is equal to P1 squared plus P2 squared square root. And that reference angle theta, and because you know it's a first quadrant vector, it's the absolute angle, and this is equal to inverse tan of py over px. So that gives you the magnitude of the momentum, the direction of the momentum, and to get the velocity, since you know that P3 is equal to M3 V3, P3 divided by M3 is equal to V3, which means P3 is divided by M1 plus M2, because M3 is the combined mass of M1 and M2.
Next to inverse tangent, what is that? Is that sheet O?
No, that's PY. Thank you. And that's problem 1. Oh, how much energy is lost? All right, let's do that. We gotta do that. Energy lost is equal to, really it's the delta E. So it is energy final minus energy initial. The energy final is just the kinetic energy of the final object, 1/2 m1 plus m2 v3 squared, minus the kinetic energies of each of the initial particles. And so that will be the difference in the energy, which is the energy lost. If I had said fraction lost, you would just take that delta E and divide it by the initial energy. Or you could have the fraction remain, which is energy final divided by energy initial. And you could rearrange this so the fraction lost is 1 minus E final minus E initial. So you can get pretty much everything you need. Fraction lost, fraction remain, energy lost, all that stuff. But in terms of energy lost, this is the equation that you need. Problem 2. So from the shore of a frozen lake, Eli Manning throws a 2-kilogram football at a velocity of 20 meters per second. So this football hold on, what are we talking about? No, this is equal to this minus that. So a person is standing on the ice and a 20 meter per second football hits him and he catches it, which means it's an inelastic collision. The coefficient of friction of the ice is 0.02. The question that I want is, or answered is, what is the velocity immediately after impact, and what is the distance traveled before the velocity of the ball and the person reach 0? So the football mass is 2 kilograms. The person's mass is 30, and he is at rest. The ball has the initial velocity of 20 meters per second. So because he catches the ball, it's an inelastic collision, and you know that the initial momentum is equal to the final momentum. The only object moving before collision is the football, m1 v1. Afterwards, the combined mass is m1 plus m2, and then we need to find that velocity immediately after impact. So m1 v1, m1 plus m2 is equal to v. And so that's the final velocity immediately after impact. Now the last thing is the person and the football are skidding across the ice. This means it's an energy problem where the energy initial minus the work released through friction is equal to the energy final. Since there's no change in potential energy, I don't have to worry about that. But what I do know is that the final energy or final velocity is 0, so that is equal to 0. Rewriting this, EI is equal to the work released through friction. Now, EI is the initial kinetic energy, the kinetic energy immediately after impact. So 1/2 m1 plus m2 v squared. So you go through all the basic motions. Sum of the forces in y is equal to 0, which is normal force minus mg, or mg is equal to the normal force. The friction force is mu sub k times normal force, which means it's mu sub k times mg. Work is force times distance. So the energy released through friction is mu sub k mgd. Mu sub k, the m is the combined mass, m1 plus m2, gd. And you get that. Now what you notice is that there is an m1 plus m2 term in both equations. So those cancel. I'm solving for d, so v squared over 2 mu sub k g is equal to d. Now all you have to do is plug and chug. The velocity comes from there. You know what gravity is. Mu sub k is given. You've got d. And that's number 2. Oh, we do have an elastic collision problem. That's nice. All right, so that's number 2. Number 3. One fires a bullet into a block of wood resting on a frictionless surface. The initial velocity of the bullet is 400 meters per second. After it leaves the block, it's 100 meters per second. Now, the key word is passes through. So initially, the velocity of the block is 0. Let me choose, I'll use capital B for block, and I'll use lowercase b for bullet. So the velocity of the bullet is 400 meters per second. Afterwards, the new velocity of the bullet is 100 meters per second. So we have to find out the new velocity of the block. It's an inelastic collision because it passes through. It's an inelastic collision because the bullet had to move the material of the block to the side. So momentum initial is momentum final. Momentum initial, it's just the momentum of the bullet. The final momentum is the momentum of the block plus the momentum of the bullet. Now solving for v sub big B prime, which is the velocity of the block, oop, not that. And that is the velocity of the block. So it is an inelastic collision, so you just use conservation momentum. To determine the energy lost is delta E, so that's energy final minus energy initial. The final energy is the kinetic energy of the two particles. and you subtract from it the initial kinetic energy, which is 1/2 mass of the bullet v bullet squared. And these are all squared as well. And that's the change. It should be negative. So if you said energy lost and the answer would be negative 30 joules, you would say it lost 30 joules. But I'd be fine with a negative sign. That's no big deal. And that's number 3. It's just a simple inelastic collision. It lets you know that not all inelastic collisions end in both objects are not all inelastic collisions are where they stick. Sometimes they pass through. And that was the lesson for this. Now 4 is me being mean. It's an elastic collision. And oh my goodness, we're going to learn why we hate this. Well, it's not that bad.
Is that BB squared up there?
Where? Here?
Yes.
M sub b, v sub b prime squared.
Primes is after it goes to
Yes. Primes are after, unprimes are before. So in an elastic collision, the energy initial is equal to the energy final, and the momentum initial is equal to the momentum final. Notice how the only elastic collision problem will ever do, I specifically say the collision is elastic. So if I am not going to put an elastic collision as a problem on the test, there may be elastic collisions in multiple choice, but not on the problems.
When you say multiple choice, so like you would just ask a question about elasticity?
Yeah.
You wouldn't have to work out.
The energy of two particles before the collision is 320 joules. The collision is elastic. Which of the following is a valid energy? 320, 0, 200, 600, 320. Because energy is conserved, the energy initial is the same as the energy after. That would be a perfect example of a multiple choice. So the elastic collision before, 1/2 m1 v1 squared plus 1/2 m2 v2 squared is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. These things don't stick in elastic collision, so you have to keep the particles separate. In energy and momentum, they're conserved, so m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. We do have one benefit. The little particle is 8 kilograms and has a velocity of 40. The big mass is 40 kilograms and it has no initial velocity. So V2s go away. The core of an elastic collision problem is the fact that everything over here and the masses are known. All of the new velocities are unknown. This is a two equation, two unknown. So what I suggest that you do is take A and solve for V1 prime. It could be V2 prime, but it doesn't matter. sub this into B and solve for the unknown. And then the last part, take this value and plug into A to get the other value. Now what I'm going to do, this is a 2 equation 2 unknown. If I had given you something, like A equals bx1 cx2 and D is equal to EX1 plus FX2, and the X's are the only unknowns, you would look at that and go, well, I could solve for that. It's the same thing with this. I mean, to make it happier for you, you could probably just write in the new values. Take M1, divide by 2, put that in there, and then you can just solve for it. It's tedious. It's simple, but it's tedious. Yes?
What did you cross out?
Oh, these? The initial velocity of the second mass was 0.
Okay, so
Yeah. And if it wasn't 0, it would have made the thing way more complex. So don't be afraid if you get a negative answer for V1. That just means that it bounced off and is heading back where it came from. That's not a big deal. So 2 equation 2 unknowns, I'll leave it to you to figure it out. All right, number 5 through 12. 13, right hand rule. We'll let you guys do that on your own. But 5 through 12, number 5, actually, since I'm going to use this sheet. You see something like this. Immediately, I think alpha is non-zero. I give you the force. I give you the radius. I give you the time. I give you the mass of the disk. I want to know alpha, and I want to know the number of rotations. So for something like this, the equations of usual suspects, sum of the torques is equal to I alpha, theta equals 1/2 alpha t squared. Granted, there's a theta naught and a omega naught t, but both of those are 0, so I'm just going to write that. And torque is the force times the lever arm, or the distance from the rotation point to the force, or FR.
For the theta, we went ahead and crossed out.
Yeah, I already crossed out theta naught and omega naught. It's Friday afternoon. We're lazy. So what we can do with this is that there's only one force, so there's only one torque. So FR is equal to 1/2 mr squared, alpha. Torque is equal to FR. I is equal to 1/2 mr squared. So those cancel, and I'm left with 2F over mr is equal to alpha. And now you can solve for that. You got F, you got M, you got R. Give me a number for alpha. Now theta is 1/2 alpha t squared, and theta is also 2 pi n. We're looking for the number of rotations. So this is 2 pi n 1/2 alpha t squared. I'm looking for the number of rotations, so n is alpha t squared over 4 pi. So you've got N and you got alpha, and that's it. Questions about this? Because really, 5 and 6 are just lather, rinse, repeats. So number 6,
So that's all we saw for 5 or 5
Yeah.
and an N.
yeah, 5, only thing in the box is alpha and N. And this will look a lot like what's going to be on the test. You'll see that symbol if it shows, or when it shows up, either on the test or the final. You'll see the symbol, you'll see symbols in the box. Solve for what's in the box. Don't put your answers in the box. Put it on the scratch work if you want credit for it.
Would that be the torque problem or the rotation?
Rotation.
Okay.
So on the test, you give us those top 3 formulas up there.
Yeah. They'll go on the equation sheet for sure.
I'm just trying to see, how did you derive like FR equals 1/2 MR squared?
Well, I is the moment of inertia of the disk. That will be on the equation sheet. Now, I will say this, a major difference between 5 and 6 on the homework and what could end up on the test is that it won't be a simple disk. It'll be a disk and a stick, disk and points, point and a stick. It'll be something where the geometry will be a little bit different. We're going to learn parallel axis theorem. It's going to happen. So be ready for that.
So FR equals I theta.
FR is equal to I theta.
I mean, not theta, alpha.
Yes.
Will the different geometric rotational equations be given to us? Like
Yes. You will be given 4 things: moment of inertia of a disk, moment of inertia of a point, moment of inertia of a stick, and the parallel axis theorem. From using those 4, you should be able to get what you want. All right, number 6. That's F. The radius is 3 meters. I'm looking for F and alpha. The mass is 300. The time is 45. The number of rotations is 45 as well. I'm looking for force and I'm looking for alpha. And it's safe to assume in both cases omega naught is equal to 0 and theta naught is equal to 0.
Should we assume that on our test?
I think it's a valid question to ask during the test. You could say initially what is its rotation, and I would say it's at rest. Most likely what will happen is I'll put it is initially at rest, which should imply omega naught is 0. You get the usual suspects again. So some of the torques, that's just FR. I alpha 1/2 mr squared and alpha. Now things are a little bit loopy in this case because I have an F and an alpha that are both unknown. So I gotta use the other equation, theta equals 1/2 alpha t squared, or 2 pi n is equal to 1/2 alpha t squared, or 4 pi n over t squared is equal to alpha. Now you can solve for alpha. Now that alpha is solved, F is equal to 1/2 mr alpha. And then you can solve for F. So you really got to kind of develop some equations simultaneously until eventually one just goes, you got everything except the one you're looking for. All right.
Why do we have the F equals 1/2 mr alpha?
Because some of the torques became FR. I became 1/2 mr squared. You got an R over here, you got an R squared over there. One of them cancels. And so you're left with F as 1/2 mr alpha. All right, number 7. Number 7 is the playground problem. In some respects, the playground problem is it's not quite alpha equals non-zero because there's no external force. There's a rearrangement of mass, and it's not quite pure rotation where alpha is 0 because it's definitely non-zero. So it falls in between, but it's still good to know. Now, initially you have 4 point masses. Each of them are 30 kilograms. So you've got a total of 120 pounds in point mass. The disc is 80 kilograms. The radius is 2 meters. The new radius is 0.5 meters. That's because they go from this to that, where there's still the radius R, but blowing it up, those points are at a new radius of 0.5 meters. The initial omega is 2 radians per second. I need to find my new omega, my new frequency, my new period. This is a conservation of angular momentum problem, or the old angular momentum is equal to the new angular momentum. Angular momentum is I omega. So L is equal to I omega, and L prime is I prime omega prime. So I omega over I is equal to omega prime. Now, once you get omega prime, 2 pi f prime is equal to omega prime. So f prime is omega prime over 2 pi. And then period, which is the inverse of frequency, just 2 pi over omega prime. So once we get omega prime, getting f prime and period prime is easy. So let's find omega prime. Omega prime is the moment of inertia times the old omega. So old, the initial moment of inertia times the initial angular velocity, and you divide it by the new moment of inertia. The old moment of inertia is 1/2 mass of the disk r squared plus 4 times the mass of a point r squared times omega, which is 2. The moment of inertia of the system is the sum of the moments of inertia. You have a disk and you have 4 points. So you just take the sum of moment of inertia of the disk plus 4 times the points moment of inertia. And you divide this by the new moment of inertia. The new moment of inertia is 1/2 mass of the disk r squared. It did not change. Plus 4 mass of the point r prime squared. So you could see how the moment of inertia changed. The disk didn't change, only the orientation of the points. The points went from exterior r equals 2 to r prime where it's 1/2. So now you've got everything in a situation where you can just plug and chug. And then you're done. You plug and chug in here, you get omega prime. You take that omega prime, you get f prime. You got f prime, invert it, you got your new period. And you're good to go. All right, questions about that? The key equation, this, knowing that L is equal to I omega, knowing that omega is 2 pi f, knowing that period is the inverse of frequency, knowing you've got conservation of angular momentum, and just being able to correctly identify your moments of inertia. All right, 8. 8 is also a conservation of angular momentum. What happens is you've got a record spinning at 50 radians per second. The mass of the record, oh wait, oh, it's the record which is at rest. The player disc is 5 kilograms. The mass of the record is 2 kilograms. So a 2 kilogram record at rest is dropped on a spinning disc. They immediately stick. What's the new moment of inertia? Or what's the new omega prime and f prime? F prime will get the same way that we got it over here. You just take omega prime and divide it by 2 pi. L is the initial angular momentum of the disk. L prime is the moment of inertia, or the angular momentum of the disk in the record player. I omega, I prime, omega prime. So omega prime is I omega over I prime. Now the moment of inertia initially, the only thing that is spinning is the player, or the player disc. So I here is just 1/2 mass of the player r squared, which begs the question, what is r? I don't think we, oh, you know what? I think have faith. So 1 mass of the player times r squared omega. Now down in the denominator, I prime, that I prime is the new moment of inertia. 1/2 mass of the player r squared plus 1/2 mass of the disk r squared. Remember those 3 types of numbers. I give you numbers that you need. I give you numbers occasionally that you don't need. And sometimes I don't give you numbers that you don't need. If we factor out the r squared in the denominator, in fact, I'm going to factor out a 1/2 and an r squared, which just leaves mp plus md. what we see here is that the halves cancel and the r's cancel, and I'm left with mp omega over mp plus md. It was intentional that the radius of the disk was never given. Why? Because it's irrelevant. So all you have to do now is plug in the masses and the initial omega, and then you've got everything that you need. You use this, and then you go there, and then you're good to go.
Get from that equation right there at the bottom right to that one.
How do I get from here to here?
Yes, sir.
The only thing that I did, the numerator is unchanged. The denominator, I factored out a 1/2 and an r squared. A 1/2 and an r squared out of this leaves me with MP. A 1/2 r squared out of this leaves me an MD. Now I've got an r squared in both the numerator and denominator. I can cross them out, just as well as I crossed out the 1/2s. And so that's what I did. All right. 9, 10, 11, and 12. Now this is what I'm going to do is I'm going to do only 2 of these, and I'll leave the other 2 to you. First reason is I got to give you something for you to work on. I can't do all of these. I don't want to do all of these. The next thing is you gotta try this on your own. So it's the same thing. What I'm going to do is I'll do problem 10 and 12 and leave 9 and 11 to you, and you should be able to figure out 9 and 11. It's the technique that I want to cover. So for number 10, number 10 is a lot like what we did in class. Well, definitely we did something like this in the AM section. The PM section, we didn't have the time to get to it. We have a force, we have a 3 kilogram mass, we have R1, where R1 is 0.2 meters. We've got R2, which is 0.3 meters. And then we have R3, which is 0.4 meters. At the end, there is a string which is tied to the ceiling and has a tension T, and there is a force F at the fulcrum. M2 is 12 kilograms. So when you're doing something like this, these torque bars, the torque bar, it'll probably have the title called torque bar. And if you see torque bar, it is implied nothing is moving. So if there's nothing moving, you can now say that the sum of the torques is equal to 0. Now what you need to do is you need to choose a rotation point. So choose a rotation point wisely. Choosing a wise rotation point means there are only 2 real locations to choose. The fulcrum here, or directly beneath the tension T. We'll choose the fulcrum. The reason why we choose the fulcrum is that the distance from the unknown force to the fulcrum, or rotation point, is 0. Any force times 0 is 0, so the torque given by F around that rotation point is 0. So we've effectively temporarily eliminated an unknown. The remaining 3 torques are M1GR1, M2GR2, and TR2 plus R3. Torque, by definition, if we're only interested in magnitude, is the force times whatever distance it is from the force to the rotation point. The distance from there to there is R1. The force is M1G. The distance from there to there is R2. The force is M2G. The distance from there to there is R2 plus R3. The force is tension. Now comes applying the positive and negative signs. You always start at the fulcrum and move out to whatever force it is you're measuring. M1G is to the left. The force is down. Thumb points up, or positive. M2G is to the right. Force is down. Thumb goes into the page, or negative. Tension is to the right, but in this case, the tension is up. Thumb out of the page, or positive. So that's why we choose positive, negative, positive as our signs. The goal is to find tension. M2GR2 minus M1GR1 is equal to TR2 plus R3. So G, M2R2 minus M1R1 is equal to T, and that is divided by R2 plus R3. And that's the tension. Now you can plug and shut. The last bit is, you know this thing is not moving vertically. So the upward forces minus the downward forces is equal to 0. I'm looking for F. So F is M1G plus M2G minus tension. And we're left with the force. And that's it. That's the whole thing. 1, you choose rotation point. 2, you sum the forces, or sum the torques equaling to 0. And 3, you sum the forces vertically to equal 0 as well. And then you just solve for whatever you need to solve for.
Can you get rid of the forces? You just do
Up and down. Up is positive, down is negative. Just like we did in problem set 5 with inclined planes and stuff. All right, 12 is a little bit weird. 12 has, it's a mobile.
It's immobile?
No, it's mobile as in like, you know, like a mobile over a crib. Like just that. And there's a part of my brain who wants to say Mobile, but that's the town. So R1 and R2 are given. R3 is given. and R4 is given. M1 is not given. The force is not given. And then over here, hanging from the right edge is another rotating or potentially rotating object. So I only know one of the masses, but I do know all of the distances. And a very valid question to ask, if I had not written it down, which I hadn't, is anything on this thing moving? No, it's just sitting there, doing nothing, doing nothing. So if it's doing nothing, you know all sorts of things. You can treat this as a rotation point. Everything that's happening up here is providing a tension on that string up. But since it is at the rotation point that we've decided, which is right here, we can ignore what's going on up here temporarily. So to simplify this, it's almost as like we have another fulcrum, M2 on the left, M3 on the right. We know that the sum of the torques is equal to 0, which is equal to M2R3, M3, oh, I forgot the G's, M3GR4. Doesn't really matter for the G's anyway. That force is to the left of the fulcrum and down, or positive. That force is to the right of the fulcrum and down, which is negative. So M3GR4 is equal to M2R3G. The G's cancel. And I'm left with M2 is equal to M3R4 over R3. And now we have what M2 is. Now what is happening is that these two masses are providing a tension in the string. So the tension up is the same as in magnitude but different directions as M2G and M3G. So the sum of the forces vertically, which is 0, is T minus M2G plus M3G. I'm sorry, minus for both. So M2G plus M3G is equal to tension. And then now that you have M2 and you've got M3, you can figure out the tension. It's this tension, the tension pulling this thing up is the same tension as pulling down on the upper end. So really what's happening now is R2, R1, tension down, M1G down as well. And then we have force pulling up. Now we get to choose another rotation point. I choose this. And you lather, rinse, repeat again. Sum of the torques is equal to 0. the two torques, M1GR1 and TR2. This is to the left and down, out of the page, positive. This tension is to the right and down, negative into the page. I'm looking for M1, TR2, M1GR1, so TR2 over GR1 is M1. Now I have M1. This is a nested torque bar problem. We first had to solve the smaller torque bar, and once we got the smaller torque bar, we work on the bigger one. Now that I have M1, the only thing I need now is F. Sum of the forces vertically is equal to 0, which is equal to F minus M1G minus tension. In the first part, tension was pulling up. It was holding M2 and M3 up. But when you're thinking from the vantage point of the upper bar, that tension is now pulling down on the bar. So M1G plus T is equal to F. And you can get F. So that's the technique. For problems 9 and 11, it's the same thing. Lather, rinse, repeat. Probably 9 and 11 are more like 10. You just have to correctly identify your torques, apply the correct signs, and then you're good to go. All right, I'm gonna shut this down, and then if we have any more questions, we'll